So far, we have discussed how particles in a medium make waves, and how to appropriately label them. In this podcast, we discuss how to describe the interaction of two or more waves. Individual waves always have the individual properties described above, but when there are two or more waves, and we compare them, we need a different set of vocabulary. Let us say that we are looking at two waves on the same plane as each other. The two waves are bouncing along, but not touching or anywhere near each other. We line ourselves up with them, so that the two waves and our eyes are in line. It is now that we can describe one wave in relation to the other. We should call one wave, wave 1, and the other, wave 2. Wave 1 is oscillating up and down, and the wave is progressing forwards. It is called a progressive wave. The second wave is progressing as well. The peaks of the waves are rising at exactly the same time, and the troughs at exactly the same time as well. The two waves are synchronized. When two waves behave like this, they are said to be in phase. The two waves overlap, so you cannot tell the difference between the two. Now, we have two different waves in the same arrangement. One wave in front of the other. Here, however, the peak of one wave is occurring when the trough of the other wave is occurring. You can see all of the peak of one wave and the entire trough of the other at the same time. These waves are still have the same frequency, but the arrangement of waves together is called antiphase. When one wave peaks, the other wave troughs, and vice versa. Points in between are described as not in phase and are linked by an angle of phase. If we look at an individual wave, we can describe the motion of the particle within the wave as a point on a circle. When the particle is at its equilibrium position, it has an angle of 0 degrees. When it is at its maximum positive displacement, it has an angle of 90 degrees. It has travelled a quarter of the way around the wave, around its oscillation. When it comes back to the equilibrium position, it has an angle of 180 degrees. It is level with its start position, but it is not in the same direction as it was at the beginning of the journey around the oscillation. When it is at a maximum negative displacement, it has an angle of 270 degrees. It has travelled 3/4 of the way around the wave. It returns to the equilibrium position and starts again at 0 degrees. When we describe the relationship between two waves, we discuss their phase in relation to their position on this circle or this wave. If the two waves are in phase, then their phase difference is 0 degrees. If they are antiphase, then the phase difference is 180 degrees. One is at the peak, so 90 degrees, and the other is at the trough, so 270 degrees. The difference between the two is 180 degrees. We can describe any relationship between two waves by the difference in their progression around a circle or a wave. When one wave is at a peak and the other is at equilibrium position but rising, the phase difference is 90 minus 0, which is 90 degrees. If one wave were to peak and the other were at equilibrium but falling, then the two waves would be either 270 degrees out of phase or minus 90 degrees, depending on which wave you consider to be first. You can also describe the phase relationship between two waves using a different nomenclature to describe rotation around a circle, the radian, but I'll save this for another time.